A faint glow older than the first stars fills the entire sky. This is the cosmic microwave background, the oldest light in the universe, and it holds the master plan for all of creation. By the end of this journey, you will understand how to read this ancient blueprint and see the origin of everything. We will explore what caused the first ripples in existence and how a hidden force is shaping our cosmic destiny. What does it feel like to look directly into the early moments of the universe? 380,000 years after the Big Bang, the entire universe was a searing, opaque fog. This was not a place of stars or darkness, but a churning sea of particles so dense that light could not travel any meaningful distance. Photons were constantly born, only to be immediately swallowed again in a frantic dance with electrons and protons. Then, in a pivotal moment called recombination, the expanding cosmos cooled just enough for a fundamental shift. For the first time, particles could combine to form stable, neutral atoms. As this happened, the universe suddenly became transparent. The light that had been trapped for eons was finally set free, embarking on a journey across space and time that continues to this very day. That first flash of liberation is what we now detect as the cosmic microwave background. It is the oldest photograph ever taken, a fossilized snapshot of the cosmos in its infancy. Though its original visible light has been stretched by the expansion of the universe into faint microwaves, it still bathes every corner of space in a nearly uniform, cold glow. This discovery was one of the greatest accidents in scientific history. In 1965, two radio astronomers, Arno Penzias and Robert Wilson, were troubleshooting a persistent, faint hiss in their giant horn antenna. They pointed it at the sky and the noise was there. They pointed it at New York City and the noise remained. They even famously cleaned out a pair of nesting pigeons and their stubborn residue, convinced this was the source of the interference. Yet the faint, universal static persisted. They had not found a technical fault. They had stumbled upon the echo of creation itself, the afterglow of the Big Bang. This accidental finding provided the first solid, observable evidence for the theory of the universe's explosive origin, completely reshaping the field of cosmology. It confirmed that we are not just theorizing about the beginning, we can actually observe its remnant light. So what profound secrets are hidden within the nearly perfect uniformity of this ancient glow? This first portrait of the cosmos reveals a universe that is just 0.003% of its current age. It is the ultimate baby picture, a direct image of cosmic infancy. But this is not a photograph in the way we normally think. The brilliant visible light from that first dawn has been traveling for so long through an expanding universe that its very waves have been stretched. They arrive at our telescopes not as a blinding flash, but as a faint, cold whisper in the microwave part of the spectrum, a uniform glow chilled to just 2.7 degrees above absolute zero. To read this ancient blueprint, we needed to map it with incredible precision. Spacecraft like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck satellite have spent decades observing this cold light, creating ever more detailed maps of the entire sky. What they found was not a featureless blank canvas. Etched into that near-perfect uniformity are incredibly subtle patterns, tiny variations in temperature that amount to mere millionths of a degree. These are not imperfections, they are the universe's fingerprints. These faint ripples of slightly denser, slightly warmer gas and slightly less dense, cooler gas are the crucial imprints of the earliest structures. They are the seeds from which everything we know would eventually grow. every galaxy, every star, every planet was once just a tiny fluctuation in this cosmic background. This detailed baby picture gives us the ultimate starting conditions, the initial state of the universe. It shows us the blueprint, but it also raises a deeper question. What cosmic force could have written these first, faint ripples into the fabric of reality itself? That persistent hiss detected by Penzias and Wilson was far more than just background noise. It is the cosmic afterglow of the universe's earliest moments, the time when the cosmos itself became transparent. To understand this transformation, we must journey back to a time before the first stars, when the universe was not a void but a dense, searing plasma. In this primordial state, light particles or photons were completely trapped. They would leap into existence only to be immediately scattered by a dense sea of free electrons, bouncing around in a frantic, glowing fog. Light could not travel in a straight line for any meaningful distance, rendering the entire universe opaque. Then came a pivotal event known as recombination. As the cosmos continued to expand and cool, it reached a critical temperature that allowed a fundamental shift. Electrons, which had been racing freely, finally slowed down enough to be captured by protons, combining to form the first stable, neutral atoms, mostly hydrogen. In that moment, the fog lifted. The sea of particles that had been constantly scattering light suddenly cleared. For the very first time, photons were set free, able to stream across the universe without constant obstruction. That first flash of liberated light is what we see today as the cosmic microwave background. It has been traveling for almost 14 billion years, and in that time, the very fabric of space through which it moves has been stretching. This incredible expansion has stretched the light's waves, transforming its original, brilliant, visible energy into the faint, cool whisper of microwaves we now detect. This direct link back to the universe's first transparent moment makes the CMB our most powerful window into the deep past. It is our only direct observation of the universe's earliest chapters. By studying its subtle patterns, we are not just looking at an ancient relic, we are testing the very theories of how everything began, and its most profound feature is a beautiful paradox. Why is this afterglow so incredibly uniform in every direction, yet imprinted with those tiny, crucial ripples that became the blueprint for all structure? Etched across the cosmic map are subtle imperfections, a mottled pattern of hot and cold spots. This cosmic speckle is the universe's original handwriting. Each tiny, warmer patch on this ancient canvas marks a region where the primordial gas was ever so slightly denser, while each cooler spot signifies a place that was a little more empty. These minute variations in temperature, a mere few millionths of a degree, are not random noise. They are the fundamental seeds of destiny. Think of this map as the ultimate architectural blueprint for our entire cosmos. On a city plan, you see small marks indicating where future skyscrapers and neighborhoods will rise. In the same way, each of these tiny overdense spots in the early universe was a designated plot, a gravitational anchor point where matter would slowly gather over billions of years. Every galaxy, from our own Milky Way to the most distant spirals, and every immense cluster of galaxies, began its life as one of these faint ripples. But where did these crucial ripples come from? The source lies in the very first moments of time. The prevailing theory suggests that microscopic quantum fluctuations, tiny jitters in the fabric of reality itself, were present at the birth of the universe. Then, in an unimaginably brief burst of exponential expansion known as cosmic inflation, these subatomic wrinkles were stretched to cosmic proportions. What was once a quantum whisper became a gravitational shout, imprinting itself as the density variations we now see in the cosmic background. By meticulously measuring the statistical properties of this speckled pattern, what scientists call its power spectrum, we can read the universe's ingredient list. This code reveals the precise amounts of ordinary matter, the mysterious dark matter that governs the growth of galaxies, and the dark energy that drives the cosmos apart. It is a complete recipe for creation, written in the cold light of the beginning. This discovery pushes our inquiry back even further, to the mysterious mechanism that planted these quantum seeds in the first place. This beautiful cosmic speckle, the pattern of hot and cold spots we see in the ancient light, had to come from somewhere. Its origin story takes us back to the most extreme moment in the history of everything, a fraction of a second so small it defies human intuition. In that first sliver of time, the universe is thought to have undergone a monumental growth spurt known as cosmic inflation. This was not the steady, gradual expansion we see today. It was a staggering, exponential explosion of space itself, doubling in size again and again in an unimaginably brief instant. During this foundational period, the very fabric of reality was a turbulent quantum sea, fizzing with microscopic fluctuations. At the tiniest scales, energy fields would jitter, creating minuscule hills and valleys in the newborn spacetime. Under normal circumstances, these quantum ripples would have faded away as quickly as they appeared, far too small to have any lasting effect on the cosmos. But inflation did something extraordinary. It stretched the fabric of the universe so rapidly, so overwhelmingly, that it took these subatomic wrinkles and blew them up to a cosmic scale. What was once a quantum whisper, smaller than a single atom, became a gravitational shout that spanned light years. These stretched fluctuations became the permanent imprints in the density of the early universe, the very seeds of slightly denser and slightly emptier regions we now see frozen into the cosmic background radiation. Without this inflationary burst, the universe would likely be a very different place, lacking the crucial unevenness required for galaxies to ever form. The specific pattern of these ripples, the statistical signature we measure, acts as a powerful piece of evidence for this theory. It strongly suggests that the geometry of our universe is flat, just as inflation predicts, meaning that on the largest scales, the rules of Euclidean geometry we learned in school hold true. Inflation provides the dramatic answer to why the blueprint exists at all. It was the mechanism that took the chaotic jitters of the quantum world and engraved them into the cosmos, setting the initial conditions for everything that was to come. With this origin story in mind, we can now decode the blueprint itself to read the universe's fundamental ingredient list. So, what is our universe actually made of? The ancient light of the cosmic microwave background gives us the definitive answer, a precise cosmic recipe read directly from its subtle patterns. By analyzing the specific sizes and distributions of those hot and cold spots, scientists can perform a census of all existence. The results are both humbling and staggering. The atoms that make up every star, every planet, and every one of us, what we call ordinary matter, account for a mere 5% of the total cosmic budget. The remaining 95% is composed of substances we cannot see directly, but whose gravitational influence is written clearly into the blueprint. Dark matter, an invisible gravitational scaffold that guides the formation of galaxies, makes up about 27%, and the single largest component, a mysterious force driving the expansion of the universe to accelerate, is dark energy, dominating at 68%. How can we possibly know this from a map of ancient light? The key lies in the physics of sound waves frozen in time. In the early universe, those regions of slightly denser gas acted like cosmic bells. The intense pressure from the hot radiation would push outward, while gravity would pull the matter inward. This created a rhythmic interplay, setting up oscillations, waves traveling through the primordial plasma. The size of the largest possible ripple these waves could create before the universe became transparent acts as a standard ruler imprinted on the sky. The apparent size of these ripples in the cosmic microwave background map, which appear as a series of peaks in what scientists call the power spectrum, is exquisitely sensitive to the geometry of the universe. A cosmos with a lot of matter would have a curved geometry, making these spots appear larger to us. A universe dominated by dark energy, however, has a flat geometry, which makes the spots appear a specific, smaller angular size. The precise measurements from satellites like Planck show us that the spots match the prediction for a flat universe, a finding that requires the presence of dark energy in exactly the proportion we measure. Furthermore, the exact proportions of the first two peaks in this spectrum reveal the amounts of ordinary matter and dark matter. More ordinary matter creates a brighter first peak, while dark matter, which does not interact with light but exerts gravity, suppresses the second peak in a specific way. This is how we read the ingredient list. The blueprint does not just show us where structures would form. It tells us with incredible accuracy what the universe is built from. We now have the complete recipe for creation, but this knowledge presents a new and profound mystery. How did these ingredients, this 5% of familiar atoms and this 95% of invisible components, work together to build the vast cosmic structures we see today? This early universe was far from silent. It was a cosmic concert hall filled with a roaring symphony. The primordial plasma, a searing fluid of light, matter, and dark matter, was alive with pressure waves. These were not sound waves as we hear them, but vast, rhythmic compressions rippling through the entire cosmos, governed by a fundamental tug of war. In regions of slightly denser gas, the intense pressure from the trapped radiation pushed outward with immense force, while the relentless pull of gravity drew matter inward. This created a continuous, oscillating battle, a booming echo that traveled at nearly half the speed of light through the fiery plasma. These are the Baryon acoustic oscillations, the universe's first and most powerful music. Then, at the moment of recombination, the music stopped, the universe became transparent, and the waves were instantly frozen in place. Imagine a gigantic cosmic gong struck at the instant of the Big Bang. For those first few 100,000 years, the sound wave traveled outward, creating a spherical shell of compressed matter and energy. The moment the music ceased, that shell was fixed forever, like a fossilized ripple in space-time. This is the distinct signature we see imprinted on the cosmic microwave background. It appears as a preferred scale, a specific size for the hot and cold spots that dot the ancient sky. The largest of these spots, the first peak in the power spectrum, corresponds directly to the distance that sound could travel from the beginning of time until the universe fell silent. This distance becomes a standard ruler, a cosmic measuring stick etched into the fabric of the universe. Astronomers now use this fossilized sound wave to measure the expansion history of everything. By observing how the apparent size of this standard ruler changes at different epochs in the universe's life, we can trace how the cosmos has stretched over billions of years. The detection of these Baryon acoustic oscillations is a stunning, direct confirmation of our models. It shows us that the cosmic blueprint is not a static image, but a dynamic recording of the universe's earliest moments. The frozen music of creation holds the key to measuring cosmic history itself, but this preserved symphony was only the beginning. Those frozen ripples of matter were the raw materials, the gravitational anchors from which the visible structures of our universe would slowly, patiently assemble themselves. That fossilized symphony of sound waves gave the early universe its structure, but it was only the starting point. The real construction began in the silent darkness that followed. For millions of years, the cosmos was a vast, featureless expanse of hydrogen and helium gas, still echoing with the faint, cold glow of its birth. The only active force was gravity, working patiently and relentlessly on the subtle blueprint. Those tiny regions of slightly denser gas, imprinted by the primordial sound waves, became the universe's most important construction sites. Their extra mass, insignificant as it seemed, gave them a slightly stronger gravitational pull. Over millions of years, this allowed them to slowly draw in more and more of the invisible dark matter surrounding them. Dark matter was the silent architect of this new cosmic order. Because it does not interact with light or ordinary matter through any force except gravity, it was free to begin clumping together long before anything else. It streamed into those overdense regions, building up vast, invisible halos and filaments, a gravitational scaffolding that stretched across the expanding universe. This hidden framework dictated where the first grand structures would eventually rise. Only after this dark matter skeleton was firmly in place did the ordinary, atomic gas feel the deepening pull of these gravitational wells and begin to flow inward. Picture one of those specific warm spots on the cosmic microwave background map, a region just a fraction of a degree warmer than its surroundings. This tiny patch, smaller than a grain of sand held at arm's length on the cosmic map, was destined for greatness. As dark matter gathered there, its gravitational pull intensified, drawing in colossal rivers of hydrogen gas. This gas condensed, fragmented, and eventually ignited into the first brilliant stars, lighting up the cosmic dark ages. These first stars then grouped together into the earliest protogalaxies. Through repeated mergers and interactions over billions of years, guided relentlessly by gravity, that single, faint speck in the ancient light grew into a behemoth, a massive cluster containing thousands of galaxies, all bound together by the immense gravity of a dark matter core that we still cannot see directly. This entire process, known as hierarchical structure formation, is the universe patiently executing its own blueprint. The great cosmic web of galaxies, with its brilliant filaments and vast, empty voids, is not a random arrangement. It is the direct, grown-up consequence of the infant pattern we see in the oldest light. Every glittering strand of galaxies we observe in the modern universe can be traced back to a specific ripple in that primordial plasma. This raises a profound question about the nature of reality itself. If the visible universe of stars and planets is just ordinary matter flowing into a pre-built structure, what does that tell us about the true architect of our cosmic home, the mysterious dark matter that shaped everything from the shadows? The silent architecture of dark matter left its definitive signature in the ancient light. The specific pattern of hot and cold spots we observe in the cosmic microwave background is a puzzle that normal matter simply cannot solve on its own. For those primordial ripples to grow into the vast cosmic web we see today, a tremendous amount of extra gravitational pull was required from the very beginning. The gentle tug from the sparse atoms of hydrogen and helium was far too weak to gather matter at the speed the universe demanded. Something else, something invisible, had to be there, providing the necessary gravity to amplify those tiny seeds rapidly. This is the strongest evidence for dark matter written directly into the cosmic blueprint. The statistical properties of the speckled pattern, the precise sizes and distribution of the spots, reveal that over 80% of all matter in the universe is this mysterious, invisible substance. It does not emit, absorb, or reflect light, but its immense gravitational influence is permanently etched into that first snapshot. Further proof comes from the subtle polarization of this ancient light, a specific directionality imprinted on the microwaves. This polarization tells the story of how matter moved in the moments before the universe became transparent. The analysis shows that dark matter, because it only feels gravity, was able to begin clumping together immediately, forming the first gravitational wells. Ordinary matter, however, was held back. Atoms were constantly buffeted by the pressure of light, a force that kept them from collapsing too quickly. This delay created a specific signature in the polarization data, a unique fingerprint that confirms dark matter behaved differently from the very start. It was the unseen architect laying down the foundational framework while the ordinary matter that would become stars and galaxies was still struggling to catch up. The entire layout of the modern cosmic web, with its vast filaments and immense clusters, was predetermined by this dark matter skeleton. The brilliant galaxies we see are simply the visible material that eventually flowed into the invisible structures built for them. This confirmation of a dominant, unseen component of reality solves one profound mystery while opening a far greater one. If dark matter shaped the past, what enigmatic force is now writing the future of the cosmos? The blueprint story does not end with the formation of galaxies. The very same ancient light that revealed the dark matter scaffolding also holds clues to a force that would one day dominate everything, a shadowy presence we call dark energy. We know the universe is expanding, but the cosmic microwave background tells us something far more profound. The geometry of our cosmos, as measured by the detailed pattern of hot and cold spots, is flat. Think of space itself as a vast, infinite sheet, where parallel lines never meet and the angles of a triangle always add up to 180 degrees. This flatness, combined with a precise census of all the matter the universe contains, creates a fundamental puzzle. There simply is not enough matter, whether ordinary or dark, to result in this flat geometry. The equations of cosmology require a third, missing ingredient to make everything balance. That missing component is dark energy. This mysterious influence was not always in control. For billions of years after the Big Bang, the relentless pull of gravity was the dominant force shaping cosmic destiny. Matter, both visible and dark, worked to slow the expansion, gathering everything together. But the ancient light, when combined with observations of exploding stars in the modern universe, reveals a dramatic shift. Roughly 5 billion years ago, dark energy began to overwhelm gravity's grip. The expansion of space, which had been gradually slowing down, suddenly began to accelerate. It was as if the universe had stepped on a cosmic gas pedal, and it has been accelerating ever since. The cold, faint glow from the beginning carries the precise conditions that allowed cosmologists to predict this stunning behavior long before it was directly confirmed. What does this mean for our ultimate future? The blueprint suggests a cosmos that will continue to expand forever and at an ever-increasing rate. Galaxies will be pulled apart from one another, their light eventually fading from view. The universe is destined to become a colder, more isolated place over immense stretches of time. This revelation from the oldest light is humbling. It tells us that the cosmos we see today, with its brilliant tapestry of galaxies, is merely a passing stage in a much grander narrative. We are living in a special era, a brief window where the universe is still rich with structure, yet we can also look back and see the clear imprint of its birth. This knowledge pushes our inquiry to the very limits of physics, forcing us to ask what could have written such a precise and powerful blueprint in the first fleeting moments of time. This profound uniformity presents one of the greatest puzzles in cosmology. Look at the cosmic microwave background in any direction, and you will find the same temperature with incredible precision. The entire sky is bathed in a nearly identical cold glow. Yet, when we trace the paths of light back to its origin, a startling contradiction emerges. At the moment this light was set free, the universe was only 380,000 years old. In all that time, light could only have traveled a finite distance, a span we call the cosmic horizon. Any two regions separated by more than this horizon distance could not have exchanged information or heat. They were causally disconnected, forever out of touch. Yet, when we look at the cosmic background, we see regions on opposite sides of the sky, over 90 billion light-years apart at that early time, sharing the exact same temperature. How could these vastly separated parts of the universe have coordinated themselves so perfectly if they had never been in contact? This is the horizon problem, a deep flaw in the original Big Bang model. The solution requires a dramatic revision of the universe's very first moments. Cosmic inflation provides the elegant answer. It proposes that before the universe was even a fraction of a second old, it underwent a period of hyper-accelerated expansion. In this model, the entire observable universe we see today, from one horizon to the other, was once contained within a volume trillions of times smaller than a single proton. This tiny seed was so minuscule that every part of it was in intimate causal contact, allowing it to easily reach a uniform temperature and density. Then, inflation stretched this infinitesimally small, connected region to a size larger than our entire visible cosmos. The near-perfect uniformity we observe in the cosmic microwave background is not a strange coincidence. It is a direct prediction of inflation, a fossilized relic of that primordial unity. The fact that the temperature is the same everywhere we look is powerful validation that our entire cosmic home once existed in a state of profound connection, a microscopic point where everything was in touch with everything else. This resolution transforms the horizon problem from a crisis into a triumph, showing how the oldest light tests our most radical ideas about the beginning of everything. Beyond the temperature map lies a deeper, more subtle layer of information encoded in the light itself. This ancient afterglow is not just a uniform color, it also carries a specific directionality, a faint polarization imprinted at the moment of its release. Think of the cosmic microwave background as light reflecting off a vast cosmic ocean. Just as sunlight glinting off water becomes polarized, taking on a specific orientation, the CMB photons were given a directional preference when they scattered off electrons for the final time. This polarization is the blueprint's fine print, a whisper of advanced physics that tells us not just where matter was, but how it was moving. The patterns etched into this polarized light come in two fundamental types. The first are E-modes, which are gentle, radial patterns like the petals of a flower or the lines of force around a magnet. These were generated by the simple density fluctuations, the hills and valleys of matter that seeded the galaxies. They are the fingerprint of the primordial plasma's basic vibrations. The second type, B-modes, are far more elusive. These are curl-like patterns, swirls in the fabric of the light that could only have been created by a far more dynamic process. The most sought-after source of these swirls would be primordial gravitational waves, ripples in space-time itself generated during the universe's earliest formative moments. Detecting these primordial B-modes is a central goal of modern cosmology. It would be like finding the first tremor from the Big Bang, a direct signal from the inflationary epoch that no other observation can provide. This deeper layer of the blueprint promises to pull back the curtain on the universe's very first instant, a time when the laws of physics as we know them were being forged. The hunt for these incredibly faint signals pushes our most powerful telescopes and our collective ingenuity to their absolute limits, asking if we can finally read the universe's very first words. To capture this ancient blueprint in its full complexity required an instrument of almost unimaginable sensitivity. The European Space Agency Planck satellite was precisely that, a technological marvel designed not to look at stars or galaxies, but to stare into the fundamental glow of the universe itself. Launched in 2009, its mission was to create the most detailed all-sky map of the cosmic microwave background ever attempted. For over 4 years, its cryogenically cooled instruments scanned the heavens, measuring the faint temperature variations and subtle polarization of the primordial light. It did not look at just one color of microwave light, but across 9 distinct frequency bands. This multi-frequency vision was its superpower, allowing scientists to perform a remarkable feat of cosmic subtraction. The cosmic microwave background is not the only source of microwaves in the sky. Our own Milky Way galaxy glows with foreground emissions from dust and charged particles. By comparing the sky across all 9 frequencies, researchers could identify and digitally remove this galactic interference, peeling back the veil of our own cosmic neighborhood to reveal the pristine, ancient signal beneath. The result was a map of breathtaking clarity, a speckled canvas showing the hot and cold spots of the infant universe with a precision of a few millionths of a degree. This was the blueprint in high definition. From this exquisite data, the Planck collaboration extracted numbers that now form the bedrock of modern cosmology. It refined the universe's age to 13.8 billion years with unprecedented certainty. It delivered the definitive cosmic recipe, confirming that ordinary matter makes up just under 5% of the universe, dark matter about 27%, and dark energy a dominant 68%. The statistical properties of the fluctuations, their specific sizes and distribution, were measured with such accuracy that they tightly constrain nearly every model of the universe's origin and evolution. The Planck dataset has become the gold standard, a reference point against which all new cosmological theories must be tested. It solidified our understanding of the standard model of cosmology to a remarkable degree. Yet, in achieving this, it also did something just as important. It revealed subtle anomalies, faint whispers in the data that do not quite fit our expectations. These curious features, like a mysterious cold spot or an unexpected lopsidedness in the temperature patterns, are not errors. They are hints, perhaps, of new physics waiting to be discovered. This incredible map, our most complete picture of the beginning, therefore serves as both a triumphant conclusion and a thrilling new starting point, pushing us to look even deeper into the story written in the oldest light. Yet for all its stunning confirmation, the Planck map holds intriguing wrinkles. Across the vast cosmic canvas, scientists have noticed subtle, large-scale anomalies, strange features that do not quite match the expected pattern of a perfectly random universe. One of the most puzzling is known as the axis of evil, a name that reflects its unusual nature. This is not a physical axis, but an unexpected alignment. The hot and cold spots in the cosmic microwave background appear to be correlated across billions of light years, lining up in a way that seems to suggest a preferred direction in space, a concept that directly challenges the foundational principle that the universe is the same in every direction. It is as if the cosmos has a faintly tilted floor, a ghostly imprint of orientation we cannot yet explain. Then there is the famous cold spot, an unusually large and profoundly cool region in the southern sky. This is not just another minor fluctuation, it is a colossal cosmic void, a vast expanse that appears too empty and too cold to be easily explained by our standard models of cosmic evolution. The simplest explanation might be a giant supervoid, an immense bubble of relative emptiness in the cosmic web. But even this idea is stretched to its limits, as the sheer scale and chill of the spot challenge whether such a structure could have formed in the time available. This has led to more exotic proposals. Could the cold spot be a signature of an encounter with another universe? an imprint left from an early contact with a separate cosmic bubble in the greater multiverse? Or does it point to a gap in our understanding of dark energy itself? The scientific consensus remains cautious. These anomalies could still be statistical flukes, rare but possible features in an otherwise standard cosmos. Yet their persistent presence reminds us that our magnificent blueprint is not yet fully understood. They are the faint, unresolved notes in the symphony of creation, hinting that the story we have pieced together, for all its elegance, might still have a few unwritten pages. These cosmic curiosities are not failures of our models, but their greatest gift, driving the relentless quest for deeper observation and more profound theories. The geometry of our universe is not a matter of philosophical debate. It is a physical property written in light. Just as a flat sheet of paper has different rules than the curved surface of a globe, the overall shape of spacetime dictates the fate of everything within it. Cosmologists have long considered three possible geometries for the cosmos, each with its own strange consequences. A spherical or closed universe would be finite, where parallel lines eventually converge and the angles of a triangle add up to more than 180 degrees. A hyperbolic or open universe would be infinite and saddle-shaped, where parallel lines diverge and triangle angles sum to less than 180 degrees. And then there is the flat universe, the precise balance point between the other two, where the familiar rules of geometry we learned in school hold true across the largest imaginable scales. In this cosmos, parallel lines remain parallel forever, and the angles of a triangle always add up to exactly 180 degrees. The ancient light of the cosmic microwave background serves as the ultimate surveyor's tool, measuring which of these geometries is our reality. The key lies in the apparent size of the hot and cold spots, particularly the scale of the first and largest acoustic peak. Think of these spots as standard rulers of a known size etched into the sky. In a spherical, closed universe, space itself curves back on itself, acting like a giant magnifying glass. This curvature would make these cosmic rulers appear larger to our telescopes. In an open, hyperbolic universe, the opposite would occur. The spreading geometry would make the same rulers appear smaller. The Planck satellite's exquisite measurements revealed the truth with stunning clarity. The observed angular size of these spots matches with incredible precision the prediction for a perfectly flat universe. There is no magnifying effect and no shrinking effect. The blueprint shows us a cosmic sheet of unimaginable vastness, yet one that is geometrically flat. This flatness is not a simple fact. It is a profound clue about the total energy content of everything. For the universe to be flat, the combined density of all its components, ordinary matter, and dark energy, must be exactly at a specific critical value. It is a perfect balancing act. Too much matter and energy, and the universe would have collapsed back on itself long ago in a fiery crunch. Too little, and it would have expanded so rapidly that no galaxies could ever have formed. The fact that we observe this precise flatness, that the total density is so exquisitely tuned to this critical value, is one of the most compelling pieces of evidence for cosmic inflation. The inflationary burst would have stretched the infant cosmos so violently that it ironed out any initial curvature, flattening it to the near perfection we observe today. This geometric certainty now anchors our entire standard model of cosmology, giving us a stable foundation from which to project the ultimate fate of the cosmos. A flat universe dominated by dark energy points toward an eternal and accelerating expansion, a future of increasing isolation and cold. Yet this very certainty forces us to confront a deeper mystery. Why does our universe possess this specific, finely tuned geometry? a flatness that seems to be a prerequisite for the complex cosmic story we find ourselves within. 13.8 billion years. This is the age of our universe, a number with immense gravitas derived directly from ancient light. But how can we possibly read this cosmic clock from a faint, cold glow that has traveled to us from the dawn of time? The answer lies in treating the cosmic microwave background as the ultimate calibration tool for our models of cosmic evolution. We do not measure the age directly like counting tree rings. Instead, cosmologists perform a masterful feat of reverse engineering. They take the detailed characteristics of the CMB, the precise statistical patterns of its hot and cold spots, and feed them into the equations of our standard cosmological model. This model, often called the lambda-CDM model, is essentially the universe's user manual. It describes how a cosmos filled with dark energy, cold dark matter, and ordinary matter will evolve and expand over time. The pattern of peaks in the CMB power spectrum is like a complex lock, and the parameters of the model are the key. The Hubble constant, which measures the current rate of cosmic expansion, the density of ordinary matter, the amount of dark matter, and the strength of dark energy, all of these are variables that can be adjusted. The goal is to find the single, perfect combination of these values that, when the equations are run backwards, reproduces the exact speckled map we observe today. When scientists from the Planck collaboration did this, they found a remarkably consistent and robust solution. The best fit values for all these parameters, derived purely from the infant universe's blueprint, point to one inescapable conclusion. From the moment of the Big Bang until now, 13.8 billion years have passed. This result is not a single, fragile calculation. It is a tightly woven web of interdependent measurements, where the value for dark energy is informed by the matter density, and the Hubble constant is constrained by the geometry, all cross-checking one another to produce a single, coherent timeline. The age is further confirmed by entirely independent methods. By dating the oldest stars in our own galaxy using stellar evolution models, astronomers arrive at a strikingly similar figure, with the most ancient stars clocking in at over 13 billion years. This powerful convergence of evidence from the very first light to the first stars gives us profound confidence. We now possess a complete timeline, a chronological narrative that stretches from an unimaginable beginning to this present moment. This is not just a number, it is the foundation for every story of cosmic evolution, the definitive starting point from which we can trace the epic journey of how a universe of smooth, hot plasma transformed into the intricate cosmic web of galaxies we call home today. That ancient, cold glow from the universe's infancy did not remain the only light for long. For hundreds of millions of years, the cosmos entered a profound silence known as the cosmic dark ages. The brilliant flash of recombination had faded, leaving behind a vast, expanding sea of neutral hydrogen gas, utterly dark and without any new sources of light. But deep within the gravitational wells sculpted by dark matter, a quiet revolution was brewing. The first stars were beginning to ignite. These were not like the stars we see today. They were behemoths, hundreds of times more massive than our sun, and they burned with a fierce, short-lived intensity. Their brilliant ultraviolet radiation acted like a cosmic blowtorch, flooding the surrounding space and persistently striking the neutral hydrogen atoms that filled the void. This intense energy broke apart those stable atoms, separating electrons from their protons and turning the transparent universe back into a plasma of charged particles. This great transformation is the epoch of reionization, the universe's second dawn. It was not a single, instantaneous flash, but a gradual process where vast, overlapping bubbles of ionized gas grew around the first stars and galaxies, eventually meeting and merging until the entire cosmos was once again filled with free electrons. This monumental event left its own distinct signature on the ancient light we observe today. As the cosmic microwave background radiation traveled through this newly reionized medium, some of its photons encountered these free electrons and were scattered one final time. This last interaction imprinted a specific, large-scale pattern of polarization onto the cosmic microwave background, a gentle swirl in the light's directionality that we can now detect. By carefully measuring this polarization, astronomers can perform a kind of cosmic archaeology. The signal acts as a timestamp, allowing us to estimate when reionization began, how long it lasted, and how quickly those first brilliant objects lit up the cosmos. This provides a crucial bridge in our cosmic story, connecting the pristine blueprint of the early universe directly to the era of galaxy formation. The second dawn of light marks the end of the Dark Ages and the true beginning of the universe as we recognize it today, a cosmos filled with shining islands in the vast dark. The precise perfection of our cosmic blueprint leads to an even more breathtaking possibility. The specific numbers we read from the ancient light, the exact density of the initial ripples, and the balance of the fundamental forces appear almost too perfect. They seem finely tuned, set within a remarkably narrow range that allows for the existence of galaxies, stars, planets, and ultimately, life. If the force of gravity were even slightly stronger, the universe might have collapsed back on itself immediately. If it were slightly weaker, no structures would have ever formed at all. This apparent fine-tuning presents a profound puzzle. Why does our universe have just the right recipe for complexity? One compelling, though highly speculative, answer arises from the very theory that explains the blueprint so well: cosmic inflation. Some models suggest that inflation is not a one-time event that created our single universe. Instead, it could be an eternal process, a forever bubbling cauldron of spacetime where new universes are constantly budding off from a larger meta-cosmic reality. This is the multiverse hypothesis. In this vast cosmic landscape, each of these universe bubbles could possess entirely different physical laws and fundamental constants. Some might expand and collapse in an instant, while others might be composed of nothing but empty, featureless space. In such an unimaginable plurality of realities, it is no longer surprising that we find ourselves in one of the rare, fortunate bubbles where the conditions are just right for life to emerge. We are not living in a specially designed universe, but rather, we are a natural outcome of a much wider, more diverse cosmic ecosystem. The cosmic microwave background does not provide direct, observable proof of other universes, as they would exist beyond our cosmological horizon, forever out of reach. However, the specific properties it reveals, like the minute amplitude of the primordial fluctuations, are perfectly consistent with the predictions of inflationary models that also naturally lead to a multiverse. This transforms our understanding of the cosmic microwave background's significance. It is no longer just the blueprint for our single cosmic home, but a potential keyhole, a glimpse through which we might infer the existence of a far grander and more populous reality beyond our own. The oldest light in our sky may be the most important clue we have, hinting that everything we can observe is just one small chapter in an infinite, ongoing story of creation. The story of the oldest light is far from finished. Our current map of the cosmic blueprint, for all its exquisite detail, is still missing its most profound signature, a whisper from the universe's very first instant. To capture it, a new generation of cosmic observatories is now being built, instruments of staggering sensitivity designed to listen for the faintest echoes of creation. On remote, high plateaus in Chile and at the South Pole, Next-generation ground-based telescopes like the Simons Observatory and the even more ambitious CMBS-4 are taking shape. These are not single dishes, but vast arrays of thousands of individual superconducting detectors working in concert to scan huge swaths of the sky. Their primary target is the elusive swirl pattern in the cosmic microwave background's polarization, the primordial B modes. This signal is the direct imprint of gravitational waves generated during inflation, ripples in spacetime itself that have been traveling through the cosmos since the beginning. Detecting it would be like finally hearing the first tremor of the Big Bang, confirming the rapid inflationary growth spurt that shaped our entire reality. Proposed space missions like LightBird are designed to complement these ground-based efforts from the pristine environment of orbit, free from atmospheric interference, to conduct an all-sky survey of this faint polarization with unmatched precision. Beyond this monumental hunt, these advanced instruments will push our understanding of the cosmic recipe to new limits. By measuring the subtle ways the CMB light is distorted as it travels through the large-scale structure of the universe, an effect called gravitational lensing, they will weigh the ghostly neutrinos that flooded the early cosmos, potentially pinning down their exact mass for the first time. They will also search for signs of other, yet unknown relativistic particles that may have roamed the primordial universe. Each incremental increase in sensitivity is not just a technical improvement, it is a journey deeper into the unknown. The relentless pursuit of finer and finer details in this ancient glow promises to test our standard model of cosmology to its limits. We are building the tools that may finally read the universe's very first words, potentially uncovering physics that operates at energies 1 trillion times higher than any particle collider on Earth can reach. This is not the end of the story, but the next great chapter in decoding the cosmic blueprint, a patient search for the final, missing pieces of our ultimate origin story. The same ancient light that illuminates our origin also reveals our ultimate destination. The pristine flatness of the universe and the dominant presence of dark energy, both read from the cosmic microwave background, sketch a future of profound transformation. According to our most robust models, the cosmos is set on an irreversible path toward what scientists call the heat death, or the Big Freeze. This is not a dramatic explosion or a collapse, but a slow, inexorable fading. As dark energy continues to drive an accelerating expansion, distant galaxies will one by one slip beyond our cosmic horizon, their light stretched to wavelengths too long to ever reach us again. The great cosmic web, with its brilliant filaments of galaxies, will slowly unravel and fade from view. In time, the fuel for new stars will be exhausted, and the last generations of stars will burn out, leaving the universe in permanent darkness. Even the cosmic microwave background, the oldest light itself, will not escape this fate. Its faint microwaves will be stretched to ever longer wavelengths, its energy diluted until it merges with the background noise of space, becoming completely undetectable. There is a profound and poetic symmetry in this. The blueprint from the first moments, with its specific balance of ingredients and its flat geometry, does not just tell us how everything began. It encodes the entire arc of the story, from the fiery dawn to the final, silent equilibrium. This cosmic narrative invites a moment of quiet reflection. Our existence is nestled within a fleeting, brilliant chapter, a window of time when the universe is both structured enough to build galaxies and transparent enough for us to look back and see its birth. We are the universe awakening to contemplate its own magnificent and ultimately transient story. This cosmic fine-tuning is not a minor detail, it is a fundamental feature of reality itself. The ancient light we have been decoding reveals a universe that seems almost perfectly calibrated for the emergence of complexity. The precise amplitude of those initial ripples, the exact lumpiness we measure in the cosmic microwave background, exists within a breathtakingly narrow window of possibility. If those primordial density fluctuations had been just a bit stronger, the gravitational pull in the early universe would have been overwhelming. Matter would have collapsed into a vast swarm of black holes, leaving no chance for stars or planets to form. On the other hand, if the fluctuations had been even slightly weaker, the gentle tug of gravity would have been too faint. Matter would have remained spread too thin, forever a diffuse cloud of gas, never gathering into the galaxies that serve as cosmic cradles. Our universe, as read from its blueprint, possesses just the right amount of initial variation to build a rich and structured cosmos without coming undone. This remarkable balance leads to a profound philosophical question known as the Anthropic Principle. In its simplest form, it suggests that the physical constants and initial conditions we observe must be compatible with our existence as observers. We could not possibly be measuring a cosmic background radiation in a universe that could not have produced us. This is not an explanation in itself, but a starting point for a deeper inquiry. Why does a universe that seems so vast and impersonal display such a precise, life-allowing recipe? One compelling answer lies in the multiverse concept. If our cosmos is just one of countless bubbles in a greater meta-reality, each with its own random set of physical laws, then it is no surprise we find ourselves in one of the rare habitable ones. The cosmic microwave background, in this view, becomes our local user manual, not a universal decree. It shows us the specific settings that allow our story to unfold, while hinting at an immeasurably vaster cosmic landscape beyond our view. The mystery embedded in the oldest light therefore deepens from a question of how our universe works to why it is this particular way at all. This impulse to understand our beginnings is written not only in the stars but in our oldest stories. Long before satellites mapped the cosmic background, human cultures gazed at the heavens and crafted creation myths to explain the emergence of everything from nothing. A recurring theme across these ancient narratives is the universe being born from a formless, dark, and silent space. In many traditions, this emptiness is broken by the appearance of a cosmic egg or a single point containing all potential, a powerful symbolic parallel to the initial singularity described by the Big Bang. Then comes the moment of light. The book of Genesis opens with the divine command, "Let there be light," separating illumination from the primordial darkness. Similarly, many Polynesian myths tell of the universe emerging from a profound night, while Hindu texts describe a golden, cosmic egg radiating light as it opens to create the world. The cosmic microwave background, that first flash of liberated photons, is science's direct observation of this very moment. It is our empirical record of the universe's own first dawn. Of course, the methods and purposes of science and mythology are profoundly different. One relies on testable evidence, mathematical models, and precise instrumentation to build a physical understanding. The other uses symbolic language, metaphor, and spiritual insight to convey cultural meaning and our place within the cosmos. Yet both are fundamentally human responses to the same overwhelming mystery, the question of where we came from. The scientist meticulously analyzing the polarization of microwaves and the ancient storyteller recounting the opening of a cosmic egg are engaged in the same essential endeavor, trying to read the blueprint of existence. This deep connection bridges millennia of human curiosity. It reveals that our drive to decode the cosmos is not a cold, purely technical pursuit, but a modern chapter in an eternal story. We are still asking the same questions, only now we have the tools to listen for the answers in the faint, cool whisper of the first light. One of the most persistent ideas about this ancient light is that we are seeing the edge of the observable universe. This is a fundamental misunderstanding. The cosmic microwave background is not a distant wall at the far reaches of space. It is quite literally everywhere. The afterglow from that first flash of liberated light fills the entire cosmos, and we are immersed in it right now. We are simply detecting it from our specific location in space and time, like standing in a gentle rain and observing the droplets that are just now reaching us. Every point in the universe has its own observable cosmic microwave background, its own unique perspective on that first dawn. It is a universal backdrop, a preserved reference frame against which the entire cosmic drama unfolds. It is also crucial to clarify that this is not the absolute oldest light from the very beginning of time. The universe was born in the Big Bang, but for its first 380,000 years, it was an opaque, searing fog. Light was trapped, unable to travel freely. The moment of recombination, when atoms formed and the cosmos became transparent, was the first time photons could embark on a long journey. So the cosmic microwave background is the oldest light that can possibly reach our telescopes, a snapshot of the universe at that specific, pivotal age. It is our ultimate observational horizon, not because there is a physical barrier, but because any light from earlier times was immediately absorbed by the primordial plasma. We cannot see beyond this surface of last scattering not because it is a wall, but because looking further back in time would mean looking into an era before light could travel at all. Correcting these misconceptions is vital because it transforms our understanding of what this ancient glow truly represents. It is not a boundary or a limit. It is the most profound historical record we possess, a preserved backdrop that has witnessed the entire history of the cosmos. Every galaxy that has ever formed, every star that has ever shone, has done so against this constant, cool glow. By understanding its true nature, we see it for what it is, the foundational canvas upon which the story of our universe is painted. This cosmic blueprint is not locked away in a scientific vault. It is a public treasure waiting for your own eyes. You can become a cosmic cartographer right now, exploring the ancient light with the same data used by professional astronomers. The most detailed map created by the Planck satellite is available for anyone to explore through the Planck Legacy Archive. With a few clicks, you can open a full-color image of the entire sky, a sphere flattened into an oval, and zoom in to see the intricate speckle of hot and cold spots that seeded all of galactic civilization. To make this exploration even more tangible, try using interactive planetarium software or web-based sky viewers. Many of these tools allow you to layer different views of the cosmos. You can pull up the cosmic microwave background as a base layer, then toggle on an infrared map of our own Milky Way galaxy. Watch as the brilliant, dusty band of our galactic home superimposes itself over the faint primordial glow. This simple act of comparison is profoundly revealing. It visually separates the local foreground of our stellar neighborhood from the universal background of creation itself. You are literally peeling back our galaxy to see the deeper universe beyond. Another powerful resource is NASA public image galleries, which often feature high-resolution, interactive versions of the cosmic microwave background map. By zooming in and panning across this cosmic canvas, the subtle temperature variations cease to be abstract data points. The warmer, reddish patches and cooler, bluish areas become real places on a map, the designated construction sites for future galaxy clusters. Engaging with this data firsthand transforms your relationship with the cosmos. You are no longer just hearing about the oldest light, you are actively examining it. You can trace the very ripples that gave rise to our Milky Way, making the grand story of cosmic evolution a personal discovery. This direct access turns the universe's master plan from a distant concept into a tangible artifact, an ancient document that you are now helping to read. The cosmic microwave background is far from a static relic. It is a dynamic and rich cosmic archive, the ultimate historical document that confirms our grand origin story while charting our cosmic destiny. We have traced its journey from a persistent hiss in a radio antenna to a detailed map of the early universe, learning to read the subtle patterns that encode the precise recipe for everything. This ancient light reveals the exact amounts of ordinary matter, dark matter, and dark energy that compose our reality. It shows us the faint gravitational seeds from which every galaxy, star, and planet would eventually grow. It has even allowed us to measure the fundamental geometry of spacetime itself, confirming a flat universe that stretches toward an accelerating future. This single, cold glow connects the frantic jitters of the quantum realm directly to the vast, glittering architecture of the cosmic web. It offers our most profound insights into the invisible dark matter that sculpts the cosmos and the mysterious dark energy that guides its ultimate journey. Our exploration of this blueprint is far from over. As a new generation of telescopes begins its work, we will peer even deeper into this light, hunting for the swirls of primordial gravitational waves that could confirm inflation. We may soon weigh the ghostly neutrino and uncover physics that operates at energies beyond any earthly machine. Let this knowledge settle not as a collection of facts, but as a profound source of wonder. We are part of a universe that has awakened to its own story, able to look back across 14 billion years and read the first words of its own existence. We would love to hear what part of this incredible story resonated most with you. Share your thoughts in the comments below, and if you want to continue exploring the universe's greatest mysteries with us, be sure to subscribe.